Okay, good. So we've just started recording. So once again, good morning, everybody. Thank you very much for signing up and for joining us today. What we're going to be looking at today is an introduction to one of the pieces of software sold by Palisade, at risk, and we're going to be looking at in the context of two of the most common uses of the software, which is to say cost estimation and risk registers. 8th of January 2015, so I feel I should wish you all a very happy new year as well, and a very successful, prosperous, happy and healthy 2015. So the agenda for today, I'm going to give a very, very quick overview about Palisade, just so you know a little bit more about the sort of company that we are. I know there's a lot of familiar faces on the webcast. It's nice to see you all again. But for those of you who don't know about Palisade, I'll give a little kind of like a couple of minutes just talking a little bit about the company, just so you know more about us. Then what we're going to look at is an introduction to probabilistic analysis and Monte Carlo simulation. So that part of the session is going to be a kind of, I suppose, Monte Carlo 101. I'll spend a little while with some PowerPoint slides just explaining what this idea of probabilistic analysis and Monte Carlo simulation means. So for those of you who have attended 5 of these sessions before and have been using the software for years, this might be a good time to, I don't know, go and brush your hair or something like that and come back in about 10 minutes. And then after we've kind of looked at some of the fundamentals, because it's really designed to be an introductory session, so it's not going to be really complex stuff, although of course you can use the software for that. I want to try and make this as introductory a level as possible, so it's as easy as possible for people to grasp who maybe haven't looked at the software before. And then we're going to look at the software, which is at risk, and we're going to be looking at two different types of application of it: cost estimation and risk registers. So Palisade, well, this is, well, it's now our 31st year. I'm used to saying it's our 30th year, but as the New Year's just passed, we're now in our 31st year. We were founded in 1984, and we're a US company, and the London office where I'm based looks after the EMEA region and India as well, and so I'm one of the business development managers, or sales monkeys if you prefer, who works out of the London office. We've got lots and lots of users worldwide. We're used by a lot of the world's largest companies, but also by a number of smaller companies as well. I don't want to give the impression that it's all about big, very large global companies. We're used often by companies with just 1 or 2 employees, small consulting companies, etc. And we're also taught annually to lots of MBA students. Now you're going to have to excuse me. I'm just going to open my window because I've shut the door to my office to keep sound out. The radiator's on and I'm absolutely sweltering despite the fact it's raining outside. You might be able to hear kind of like a little trickling sound. Sorry, that's actually my boss calling at an inopportune time because he doesn't realise that I'm doing a webcast at the moment. He's in India right now. So in terms of our client list, in fact, to stop that happening again, what I'm going to do is I'm going to quit Skype. Not that you should ever quit Skype on your boss, but I don't want him to disturb this webcast for everybody else. So yeah, some of our clients, some of our larger clients are printed on the screen. So a lot of fairly recognisable logos. We sell to lots and lots of different industries: banking, finance, insurance, healthcare, oil and gas, mining. Kind of you name it, we sell to lots of different companies. Worldwide, our largest vertical market is probably oil and gas, followed by insurance, but you kind of have regional variations. So mining, for example, in South Africa would probably be our largest vertical market. And along with doing software, which is the kind of the basis of the company, we also do training, we do consulting, and we also do custom solutions as well, which I'll try and spend a couple of minutes on at the end, because I tend to forget to do it in these demonstrations, but I think it's actually a really useful thing to share with people who may not otherwise know about it. So what Palisade make? Well, we make a set of 7 different tools, and the different tools give different types of risk and decision analytical capability within Microsoft Excel. So they all add some functions into Excel which enable you to do things that are otherwise quite difficult or impossible to do otherwise. So the one which I'm going to have to, I know what I'm going to do, I'm going to turn the radiator down, and then I'm going to shut the window a little bit because I can hear a bit of a trickling sound, so I'm sure you guys probably can as well. Okay, so the one which we're going to be concentrating, I've also got a very squeaky chair as well, in case you didn't notice that. The one which we're going to be concentrating on today is at risk. So at risk is about this technique called Monte Carlo simulation in Microsoft Excel, and also links up to projects as well. So the idea of at risk, and I'm going to be obviously talking about this in quite a lot more detail as we go through the next 90 minutes or so. But the whole idea of at risk is that it uses these things called probability distributions which enable us to I suppose capture and model uncertainty within Excel, and what this enables us to do is to really generate lots and lots and lots and lots of different scenarios to give us a probabilistic view on things rather than a deterministic or static view. And hopefully by the end of this session, you'll kind of, if you're new to this and at the moment you're looking at this screen saying I've got absolutely no idea what any of that means, hopefully by the end of this session you'll have a better idea about what at risk does. So the starting point is really Microsoft Excel. I'm also going to, right, I promise you this is going to go smoother soon. I'm also going to forward my phone as well, so I don't keep getting people bringing me as well. Okay, hopefully that's it. Someone's obviously going to knock on the door now with a cup of tea for me or something like that. But the starting point is really Microsoft Excel. And the reason we sell to so many different companies is because our tool adds some functions into Excel that aren't there normally, and so it can really be used in any industry and lots and lots of different applications. And so typically how you build up an Excel model without at risk is by the use of point estimates. So we would put in our point estimates, whatever they are, whether they're price, volume, cost, revenue, duration, whatever. We'd put these in, we'd build up a static deterministic Excel model, and from that we'd derive various project metrics, so whether they're costs, whether it's a start date or a finish date to a project, or the MPV or the rate of return, or how much oil is in the reservoir. And these are what we would then call deterministic values. So we would typically have one scenario, one kind of number at the end of it, or maybe three at a push. And the kind of the big issues with this are really about how we can be confident in the numbers that we put into the spreadsheet. So none of us have presumably got any kind of time machine. None of us are able to see into the future, and so it's very, very hard to describe with any kind of utter certainty or accuracy what's going to happen in the future. And because of this, the models that we make are inherently wrong, basically. So this is a quote from a statistician who was kind of busy during World War II testing, I think, poison gas on rats, and he kind of developed some various ideas about statistics. And one of the kind of famous quotes is that he said that all models are wrong, but some are useful. And from Palisade's perspective, and what you'd use at risk for is to make the models less wrong and more useful. They're still going to be wrong, but they're going to be hopefully a lot more useful than they would be otherwise, and that's kind of what I want to show today. So a little example I use is the journey time to work, and so apologies if you've seen this a few times already, but I kind of live, I don't know, 15 miles from the office, and I have two modes of transportation. Normally I cycle into work. I really enjoy cycling. I get to work feeling reasonably refreshed, if not a little bit sweaty. But there's other than motorists in northwest suburban London trying to kill me, it's actually a fairly relaxing way to get to work. And one of the reasons why it's so relaxing is because I kind of know pretty much how long it's going to take me to get into the office. And so you could, if you said to me how long does it take you to get to work, if I'm cycling, I could be pretty precise, and I could say, look, somewhere between 40 and 44 minutes, something like that, 45 minutes. There's various factors which can affect me, what day of the week it is, so how many times I've cycled already, and how my legs are feeling, what the wind is like, whether it's humid or not, lots of these different things. But there's still not an awful lot of variation in the journey time to work. Sometimes it can take a little bit longer, but I've got a pretty good handle on how long it takes. When I drive to work, on the other hand, this is often what my journey looks like, and ironically I drove to work this morning because I had to bring some stuff into the office with me, and this is pretty much what my scene was like this morning when I came into work. I got into work half an hour later than planned, and so actually I was planning to rework some of this example and didn't actually have time to do it because I was stuck in traffic this morning. And so if you ask me how long it takes me to get into work when I drive, I kind of almost have to shrug my shoulders and say I really don't know. I could maybe take a punt at maybe an average time of say 55 minutes, an hour, something like that. But really, there's a huge amount of variation, and to illustrate what that variation might actually look like, this is some journey times. So this is 300 journeys to work. This isn't actually real data. I kind of like to say that I'm not the sort of sad person who actually records all these things and writes them all down, but funnily enough, I've actually decided to start doing that with my cycle times to work, and I'm plotting lots and lots of different factors on there because I want to use some of our other tools, and when I've got a bit more data to do some various analytics. I'm going to use neural tools and stat tools to do some other analysis, which seems to me to be getting more and more geeky as I get older, which my wife would definitely agree with. But this is journey time to work. So this is some sample data. I think it's pretty realistic actually of how long it takes me or how long it would take me to get to work on 300 separate occasions. And if we kind of made that into a nice looking graph, which doesn't kind of hurt your eyes to look at it might look something like this. And so that journey time to work is really an example of a distribution. And here the kind of average time might be somewhere around 55 minutes. Actually, I think if you kind of looked at this graph, the average is probably more like 65 minutes, something like that. But the average time is around about 55 minutes. On a good day, and when I say a good day, I mean a day when there's no school kids and there's no red lights catching me out, and you know, and the traffic's moving quite freely, I can do it in less than 40 minutes. On a bad day, it can be more than 2 hours. Today it was probably around about here. So reasonably painful, but that's commuting in suburban London for you. And the reason I'm kind of been waffling on about this and kind of telling you in detail about my journey time to work, and some of you are probably thinking, what on earth is this man talking about, is because I wanted to just give an example of one of the issues with deterministic thinking, which is that sure, we can talk in terms of averages, we can talk in terms of, yep, you know, the average time is 55 minutes, and actually over, you know, if we have a portfolio or a large number of samples, then indeed we may have an average of 55 minutes. But if I can't even really be certain how long it's going to take me to get to work, then when we start to kind of look around us in our work lives, then when we start to build up Excel models, it's really very, very important to accept that things that happen in the future are outside of our control. And so the best that we can do is to try and understand where that uncertainty lies, to model that uncertainty, and then to incorporate that into our models and our decision making and thinking. And so when we kind of start to look around, as I said, you start to see these probability distributions everywhere. And so cost is, you know, one of the things that we're going to be looking at today, but revenues, risk events, bad weather delays or earthquakes or what have you, durations, you know, these probability distributions kind of exist pretty much everywhere you look. And the idea of at risk is that we incorporate these into our model. Now, what does that give us? Well, probability distributions on their own aren't really all that useful to us from a modeling context, because, you know, they don't really give us much in the way of actionable information on their own. And so that's where this technique of Monte Carlo simulation comes in. So probability distributions and Monte Carlo simulation are two kind of separate things. So the idea of Monte Carlo simulation, it came out of World War II, the end of World War II, the Manhattan Project to develop the atomic bomb. And the the nuclear physicists who were working on this this project in Los Alamos, I guess, were trying to ascertain how useful the radiation shielding would be against neutrinos, and they realized that they couldn't really derive it by conventional means because there was just so many different variables at play. And so one of them had the idea of simulating it. And the name Monte Carlo came out of the fact that one of their uncles used to gamble quite heavily in Monte Carlo. And the picture of the roulette wheel here, we know with a roulette wheel that there are 36 black and red squares, and then 1 green square. So there's 37 squares, and so you know that you've got a 1 in 37 chance of hitting any number, and those are the kind of odds. And so if you kind of put a ball into a roulette wheel, let's say 370 times, then you'd expect to see maybe somewhere around about 10 for each. I mean, the more samples that you take, the more likely it is that you're going to reach or converge upon the theoretical odds. But that's the kind of the idea. So there's a 1 in 37 chance. And so this is this idea of simulating. So putting that ball in 370 times and then making a note of the squares that it lands on those 370 times, that would be an example of simulation. And the idea of Monte Carlo simulation in the context of at-risk and with modern computing is that we put in probability distributions, and then the software samples from those probability distributions over and over and over and over again. So it's generating lots and lots and lots and lots and lots of scenarios from each of the probability distributions and putting them back into the model, which is what I'm going to show you in a little while. And I'll send around this PowerPoint afterwards to anybody who wants it, so I won't kind of like just read text off the screen. But what that then gives us, so this is kind of at risk. You've got the at-risk toolbar here. So we have our probability distributions. We have the same inputs to our model, but now they're probabilistic. We then run a Monte Carlo simulation, and then at the end of it, our project metrics are probabilistic and more useful. So we get to see things in ranges. We get to see risks and opportunities and sensitivities and scenarios and so on, which is what I'm going to be showing shortly. So just wanted to give a little bit of an overview about the kind of the theory behind it, so that then when I start showing the software, hopefully you've got a slightly better idea of what I'm talking about. All this, hopefully, you'll see throughout the course of the demonstration. Some of the benefits, it's about making models less wrong and more useful, and being able to ultimately make better decisions at the end of it. So let's let's take a look at the software now. Okay, so as always at this point, whenever I minimise the PowerPoint presentation, I feel compelled to apologise for the very unprofessional looking desktop. This is myself and my daughter, and happily this is actually a shot of my office as well, so you get some idea of where I'm sitting at the moment in this squeaky chair here. I haven't got a coffee from my Nespresso machine, unfortunately, and nor do I smoke. These were something I picked up duty-free for a friend on one of my business trips. But let's load up the software. So people who have been attending these seminars for the last couple of years have quite literally seen my daughter grow up over the course of these photos. I've had photos of her from the age of pretty much 0 up to 2.5, where she is now. So what am I actually doing? Okay, I'm loading up at risk. So there's still probably a few cobwebs left from the new year. I think this is actually the first time I've had occasion to load up the software since the new year. So what I've just done, I've just clicked on the at-risk icon, and you'll see that what's happened is that the software has loaded up Microsoft Excel, and what it's done is it's added some additional functions up here into the Excel function library which weren't there previously, and these kind of behave exactly like any other Excel functions, so they're now kind of properly in the Excel function library, and so we can use the at-risk functions in conjunction with all of the other functions in Excel and vice versa. So however complex your Excel models are, and I'm sure a lot of you have got very complex Excel models. I myself am a fairly mediocre Excel modeler, but I'm sure there's a lot of people out there who use some of the kind of weird and wonderful functions in Excel which I kind of barely understand. But so however you use Excel, whether you use min-max functions, lookup tables, sum ifs, indirect, offset, any of the kind of Excel functions can be used in conjunction with at-risk and vice versa. So what I'm going to do, I'm going to load up my first example model. I'm probably going to show you maybe 3 example models today. And the first one I'm going to start off with is a little example of a cost estimation model. Now actually at this point, let me just double check to see I've got no questions. Thanks Rob, someone is saying it's beautiful weather in Edinburgh despite the reputation. Someone else is saying there's intermittent sound issues. Now the fact that only one person has mentioned there's intermittent sound issues would unfortunately suggest that Christophorus, that maybe you've got some kind of an issue with your internet connection, because everyone else tends to complain loudly and vociferously if they can't hear me. So just the one of you complaining means unfortunately you've probably got something slightly wrong with your connection. So yes, so where was I? This is a simple little cost estimation model. I always try and show fairly simplistic models to certainly to start off with, because actually how we use the software, the methodology and we would use the software is the same whether we've got a simple little cost estimate model like this with 8 line items, or whether we've got a 20,000 line item model with spread across multiple workbooks, etc. How we would use the software is fundamentally the same. So and of course, something else to state at this point is that this is just an example model. Some people, when they first see the software, they assume that what they're looking at is a kind of like a fully fledged system that's already pre-built, and that it doesn't really do exactly what they need. And really, the software is if you think of Excel as a toolkit, which you can kind of build up to make models, however weird and wonderful and fanciful that you want them, then at-risk is just really another tool in that toolkit, which just enables you to do some other things. And so yeah, this is a little cost estimation model. We've got 8 different cost elements: land, buildings, raw material, which we need to fulfill as part of this project. Each of them has been given a base case cost. So this would be an example of a single point estimate of a deterministic or static model. And at the end of it, what we've got here is this total project cost is 18.5 million. And it's fair to say that lots of companies still kind of make decisions based on this kind of idea of deterministic modeling, but there's I'm biased. I work for a company that makes software that does probabilistic analysis, but logically I think that there's quite a few issues with this approach. Not being able to sort of forecast with any accuracy how much each of these items cost is a real handicap, and so what some companies then do is the next kind of step is to build up something like a 3-point estimate to give some idea of variation or variability. And so now what we've got, along with the base cost, which we've also said is just the most likely value here, we've also got a minimum and a maximum. So now we have a bit of a range of values for each of the costs. And so some companies would just add up all the minimums or add up all the maximums and factor that into the decision. But actually that's also kind of not an ideal way to do things, because first of all we're showing for each of these scenarios is each of these cost elements is 3 different scenarios, where in reality there's probably a whole range of possible outcomes. The other factor is that if we kind of look at these, adding up all the minimums, all the maximums, and kind of getting these values down here, then that doesn't really give us a particularly well, it doesn't give us a remotely accurate picture on what the best or worst case scenario is actually likely to be. Because if we're building up a cost model and we say, okay, the maximum cost is 2.8 million, the minimum is 1.5 million, then that 2.8 million, because it's the absolute maximum that we're looking at, then that's a pretty unlikely scenario in itself, if with the caveat if we've built the model up correctly. because this is an extreme value. So the probability of this actually being 2.8 million should be really very small, because that's the extreme value. So the probability of two extreme values happening together is really small, and so on, kind of down the list. And so the probability of all these events, all these well, the bad scenarios for us if we're looking to build this project, all of these things being at the top end of things is incredibly low. And so the reality is it's going to be somewhere between these two, and so what the software is going to help us do is to start to look at that with a bit more confidence. So let's start looking at risk. The way at-risk works is that wherever we have a model, within that model, if there is any uncertainty, we look to put in probability distributions. Now, here we've got 8 different cost elements. We can see here that we've got some uncertainty around how much each of them are. So for each of these costs, I'm going to replace the fixed values with a probability distribution. So if I click Define Distributions, and so this is a cost model, so that other models are very much available. But what we have now is we have a what we call a distribution palette, which now shows us all the different at-risk distributions. So there's lots and lots of different ones on here, which is something which sometimes freaks people out if they're new to the software. Oh, there's all these probability distributions, how do I know which one to choose? And I'm sure that some of you will be sitting on here hoping for the holy grail, which is where I say this is the right distribution that you should always use. But the reality is that there's often no absolutely correct distribution. Sometimes it's about choosing the best one, or one which is appropriate, and not getting too hung up on which one. You know, the reality is that between a PERT and triangle, is there that much different? Probably not. So I'd guess that maybe 99% of our customers, possibly even more than that, don't go beyond this tab here, where we've kind of selected some of the more common ones. From a cost estimation perspective, there's, we might use a PERT, we might use a log normal, we might use a triangle, a trigen, a uniform. Any of the others? Probably not really. I don't tend to see it very much. Sometimes a normal, but I fundamentally disagree with a normal distribution being used for costs, which I'll maybe come on to in a little bit if I've got time to get on my high horse. But distributions are split into 2 different groups. You have your continuous distributions and your discrete distributions. So discrete distributions are typically used for modeling risk events. So, what's the likelihood of an earthquake happening? How many bad weather delays am I going to get in a particular time period, and so on. Continuous distributions are typically used for modeling things like cost and duration, etc., where we have a whole range of values, such as we have here, between 1.5 and 2.8 million, and anywhere along that range is theoretically possible. Now, in terms of the kind of choice of distribution, there is a lot of information available on the internet about what sort of distribution is the best one to choose. You've got some help in the software. Wherever you are in the software, if you see one of these little red circles, that means that there's a link to a help, like a fully contextual help file. So if I click that, then this will go in and it'll tell me about a triangular distribution, a description, some examples, the various statistics behind it, and so on. So let me just have a little gulp of water. So by the end of this, I'm probably going to be really hoarse. So the software can give you some help. There's we've got user forms on our website where you can go and post a question in there. There's various presentations available for download from our website as well. If you've got historic data, you can use the historic data to find out what distribution best fits that data and use that as a prediction. I'll show that a little bit later on. And of course, going back to the training courses which we run on a regular basis, one of the key takeouts from the training courses we run is about choice of distribution, so helping you to understand how the different distributions work. And indeed, once you kind of start to get how the different distributions work, it does all become quite a lot simpler. I do agree. For now, I'm going to use a PERT distribution. The reason I'm going to use a PERT distribution is because conveniently, like my 3-point estimate here, the parameters which we need to supply for a PERT distribution are a minimum, a most likely, and a maximum. So if I just click this little button here, which allows me to assign Excel cell references as arguments for my distribution, and then say 1, 2, 3, and then hit the enter button, let's give it a proper name as well, let's call it land. So what I now have is a distribution for the cost of my land. So if I just click on OK, what At-Risk has just done, it's now populated this cell here with that distribution. So we can now see that in this cell we've got a PERT distribution, and this risk name bit was just kind of generated when I said, okay, I want this to be called land. So it's all function driven like Excel is normally. And so in this cell I've got a distribution for land, and if I just start tapping the F9 key gently, you can see that what's happening is that the value in that cell is now changing. And so rather than having 1 or 3 values for the cost of land, now I'm generating this dynamic set of values, or rather At-Risk is, from that probability distribution. So what does that mean exactly? Well, if we go and take a little look at the distribution in a bit more detail. So the parameters, the minimum, most likely, maximum. So there was a minimum of 1.5 million, which was this point here. There was a maximum 2.8 million, which was this point here, and then there was a most likely value of 2 million, which was this point here. Now, oops, what am I doing? That's the wrong button. So what the software is doing, when I was pressing the F9 key, what the software is doing, it's taking samples from all across the distribution. So it's taking them from here, from here, from here, from here, from here, from here, and basically it's going around and it's generating scenarios or samples from this probability distribution, and it's generating them based on the shape of the distribution. So these areas out here, sorry, it's quite hard to draw with this little widget. These we would call the tails of the distribution. So these are the areas where they're less likely to occur. And indeed, that's kind of reflected in the number of samples that are going to come from that particular region. So what I've just kind of circled there are the tails, where we've got the 5th and the 95th percentile. And I'll talk more about these percentiles as we go through, because it's a fairly important point. But what this means is that when the software was taking samples and that blue cell was changing, and the values that were being returned to Excel were changing, these percentiles or confidence intervals up here are telling us how likely it is that a sample is going to come from a particular part of our distribution. And so what this is telling us is that there is a 5% chance that the cost of land is going to be between 2.469 and 2.8 million, and there's going to be a 5% chance that it's going to be between 1.5 and 1.672 million, and then there's a 90% chance that our samples are going to come from this kind of large area here around the mean. And so if I kind of grab these things. These are called delimiters, by the way. Let's say I want to find out my 90th percentile. My 90th percentile will be 2384, because there's a 90% chance that the samples are going to come from below this value, and a 10% chance that they're going to come be more than that. So that's what the software is doing. So it's taking samples from the distribution and it's putting them back into the spreadsheet. And the samples are based on a combination of the parameters up here and then the shape of the distribution. And so just to give you an idea of what a different kind of distribution might look like, if I overlay, let's say, a uniform distribution. A uniform distribution is one which is sometimes used by customers. We would typically call this one where you don't really have an awful lot of knowledge. There are some kind of uses where a uniform distribution is an absolutely valid one to use, but for the most part it's one where you're not really sure exactly what's going to happen. And the uniform distribution approximates the RAND function within Excel, and you can hopefully see that with this, if we then take samples, we take a sample from here, from here, from here, from here, and the samples are just as likely to come from anywhere on the graph as another place. So you have this straight line that goes kind of it was a straight line until I started trying to draw it. You have a straight line that goes across here, and so the samples are just as likely to come from any part of it. You haven't got this with the PERT distribution, you have this bias towards this kind of middle point here, whereas with the uniform distribution it's just a straight line. And so what that means is that the tails are emphasized a lot more, because there's a higher area, a surface area, for the samples to get taken from. This idea of kind of shapes and sampling is a very difficult one to get your head around at first if you're new to this. So I do apologise if this all sounds a little bit weird, kind of putting shapes into your computer and then on the basis of these shapes making some decisions about multi-billion-dollar projects. But it's a proven methodology that has been adopted by an awful lot of companies around the world. And what you can hopefully see is that, as I said, the uniform distribution, the tails are emphasised a lot more. So there's this much greater upside. So you've got a 10% chance that we're going to be more than 2384 with a PERT, or a 32% chance of that with a uniform distribution. And correspondingly, there's a larger chance of a downside down here as well with this one. So the choice of distribution is an important one. Even if you just use uniform distribution throughout, it's probably going to give you a better result than just deterministic modelling. So let me just speed things up a little bit. What tends to happen with these demonstrations, I do tend to start off very, very slowly, and I'm trying to build the foundations of what's going to come next, because we're going to kind of speed things up a little bit, and we're going to start talking about some quite a lot of concepts as we go through. So what I've just done, I've just dragged down those functions. As I said, because it's all Excel based, one of the nice things is that we can just drag and drop or copy and paste. So rather than having to fill things out individually, we've now got a distribution for each of these 8 cost elements that have been based on the cells here. So now what I'm going to do, I'm going to add these up, and then I'm going to select this as something called my risk output. So this is my total project cost, and what I'm now going to do, I'm going to ask at risk to take 10,000 scenarios for my project cost. So if I click Start Simulation, so this is in demonstration mode, so it's running pretty slowly. I like to show it in demo mode at first, because what you can hopefully see in the background is those samples are being generated. So the samples are being taken from each of these probability distributions. They're being put back into Excel. The sum function in Excel is then given us this value here, and that value there is then driving this histogram. So if I just speed it up, okay, so what we now have in this cell down here is not one scenario, not 3 scenarios, but we now have 10,000 scenarios for our project cost based on the uncertainty which we've put in to our model here, and the sampling. So originally the project cost was 18.5 million. That was our initial budget. Okay, we've got a 26.5% chance that we're going to come in under budget on this particular project. What's the probability we're going to be more than 20 million? Well, we've got a 1 in 5 chance roughly that this project is going to cost more than 20 million pounds or dollars or euros or whatever. This is the kind of the best case scenario. This is the worst case scenario up here, and we've got lots of different statistics along here which can be used to kind of show different things, the percentile values, etc. At its most simplistic, this is what at-risk does. We take a model, we put in probability distributions, we run a simulation, and then we look at the results, and then ultimately we make some decisions based on those results, and those decisions now have an extra dimension to the deterministic value, because it's all very well saying, okay, this project is going to cost 18.5 million, but if you go and say, I'm confident that if you give me 18.5 million to spend on this budget, then actually we've only got a 26.5% chance of coming in at less than that, then that's a very different story. And so it's about at risk is about assigning confidence levels to our outputs, to our models, to our metrics, whether it's MPV, whether it's cost, whether it's a risk register, etc. So to be able to say, to give a level of confidence in our estimates. Now, there's different ways we can display this. This is what we call a histogram. I very much like a histogram. I'm very used to it, but some people prefer an S-curve, which shows exactly the same information. It's just displayed in a different way. So there's still a 26.5% chance of coming in under budget, but this is now just an S-curve rather than a histogram. And often, kind of cost engineers prefer the kind of cumulative costs. Indeed, you could have one over the top of the other if you particularly wanted to. Now, let me just check about questions. I'll take a minute to read these. Okay, so yep. What I would do at the end of the session, we'll get this uploaded to YouTube and to our website, and then I will send around a link to download the session, and I'll basically, to anyone who signed up, I'll send around my contact details, etc. The PowerPoint is a bit heavy. It's about 6 megabytes or something like that. So I'll do the PowerPoint will be available on request, but I'll email everyone who's signed up, and so you'll have the opportunity to download this presentation and the PowerPoints as well. Can we see the questions asked by others? Do you know what? I'm not actually sure that you can. In some ways, I prefer. Maybe you can, Avni. Maybe you can tell me if you can see the question that you've just asked. So yeah, you're right. Actually, I should read out the questions so that you can see them, or rather that you know what I'm answering. So someone is asking, how did you draw the PERT distribution from the data? Do you mean this little gadget I have here, which I'm kind of like, oops, well, I'm kind of drawing on the screen. I'm not sure if you do or not, but that's a little gadget called Zoom It, which is very useful. If you wanted to see where the PERT distribution was coming from, let's have a look. See. So the PERT distribution, I just highlighted the distribution, and there we go. That's the PERT distribution in there. Someone's asking how do Palisade tools compare to companies like BWise and Thomson Reuters. Well, BWise I think is a kind of like a fully fledged risk management system. So it's what's really important to understand about at risk is that it's in its most simplistic form. If you buy it off the shelf, then what you get is you get a piece of software which gives you some extra functions in Excel, and then just as when you build up your own Excel models for cost or whatever it is for risk registers, you need to build that model yourself, and at risk functions in that way. So you still need to build up your own models, and so you add the software to that. We can help with that. We build lots of models for clients. We build lots of systems for clients as well. And this is something I was going to talk about at the end. But actually, I might as well mention it now because I'll probably forget at the end. So it's a useful thing to say. But when you use at-risk, lots of customers use at-risk like this. They add the software. They load up software. They add distributions to their models. But not all companies like to do that. Not all customers like to do that. Some customers aren't comfortable with building things in Excel. Some customers are worried about corporate standards, etc., etc., etc. So what we can also do, if I just minimize this somewhere, is we can also kind of build up models as well. So this is a fortunately it says confidential, but I've stripped out all of the customer info in here now. But we can also kind of build things up for other clients as well. You know, we can build things up so it's a form-based approach rather than Excel. So instead of having to build up Excel models from scratch, we can build systems for customers where we have these forms, and so instead of putting in, needing to type in a risk Poisson distribution or whatever it is, instead you get to do it kind of almost like a wizard approach going through. So that is something that we can do as well. Now, what other questions have we got? I suddenly got barrage with questions. Can you please explain the simulation and how to start the simulation? Okay, so to start the simulation, all we do is we select a cell to use as the output, which is what we do when we click on this add output function here, and then you select the number of iterations. Now, iterations, that's the number of samples. So when we've got 10,000 iterations, that's how many samples that we're going to run. And then we just click the start simulation button, and then the software starts. Someone else then asked any input on the number of iterations which works best. The number of iterations, so lots of people think that the maximum number of iterations you can have in here is 10,000 because you've only got this pre-built limit of 10,000 here, but actually this is a free number field. So if you wanted to give 100,000 iterations or 2,501 iterations, you can type that in. Lots of companies have a standard of somewhere between 1,000 and 10,000, but the right number of iterations depends very much on your model. So if you have a very large model where you've got lots and lots and lots of uncertainties and you have a very wide range of different possibilities, then to capture all of the different combinations of those, you're going to need more iterations. But there's so if I show you here, so next to this settings word, you've got the simulation settings option. Here you can actually go in and you can do convergence testing, which basically enables you to find the optimum number of iterations based on these different kind of inputs, etc. And so the software will tell you automatically, or you can go to auto up here, and then it will tell you what the ideal number of iterations is. Generally speaking, that's also something you can test yourself. You can do like 10,000 iterations, and then you can run 100,000 and compare the results and see if they're much different. Can we see the most sensitive factors to an output in the same way that can be seen in top rank? Yes, absolutely. I will show you that in a moment. Someone else is saying, I've got so many different questions here. Can you please discuss how to model risk events? Certainly, that is something that is going to be coming up. What else? Do you sell standard risk register products which can be further customized by the user? Yes, we do. We're actually just that's something that we're now doing. If you want to send an email in about that, what I'll do, as I said, I'll email all the sign-ups at the end. And actually, I'll also just send around my email address as well. I'm going to send everyone my email address. Any questions that I don't get around to, there's a lot of questions, I don't want to kind of like get too derailed, but any questions I don't get around to, anything else that occurs to you, please send me an email, let me know, and I'll answer you, or get one of the other sales guys here to answer you. Can you sum data from each distinct iteration? Yes, absolutely you can. Up here you've got this little X and I is the simulation data. If you go in here, you've got all of the simulation data for each iteration. You can export that to Excel or do whatever you like with it. So yes, you could do that, and you could also pull that back into your model if you wanted to as well. How does the individual probabilistic cost differ from the RAND option in Excel? Well, the RAND option in Excel is a uniform distribution, so it's the same as the uniform distribution I showed, where you have a straight line. And what we've done here is we're using a PERT distribution, which gives you this bias towards this most likely point. So if all of your distributions follow a RAND distribution, or a uniform distribution, then you could conceivably use the RAND function in Excel, but there's a whole lot more that you can do with that risk, which I'm going to show you as we go along. Someone says, I've missed the heat map and risk register part. Is there any probability of us going back to that part quickly again? not at the moment, because we're going to run out of time pretty quickly otherwise. But the whole point of that was that we can build up these customized things for customers. Someone else is saying is bespoke in the interface common, reasonably common. I mean, it's, you know, you need to have development skills to do it, but it's something which can be done. You have in At Risk, you've got a full developer kit here, you've got an automation guide, and you've got lots of different functions which you can call out and use as macros, and one of the things that you can do with that is to customize the interface. So you could, for example, lose a number of these different icons up here, or create some different ones or whatever. Please can you tell the criteria for selecting the best probability distribution? I really haven't got time to go back to that again, I'm afraid, but I kind of gave a little brief overview about it. In short, there's not necessarily a right answer. What I can do is, if you email me about this, if you want presentations, I've got a couple of presentations that I can send as well about selecting the right distribution. In your opinion, demand follows which distribution? That's a question. Well, it depends. Demand for what? It could be a number of different things. Typically, you're also going to have some correlations in there linked to price and so on, which is something I might come back to. Someone else has asked, can I be included in the list of people that receive access to the recording? Yep, everyone will get emailed about this. There's an awful lot of questions here. This is nuts. If I use, instead of cost elements, the cost of risks, how can I take into account the probability of each risk? Well, we'll look at risk probabilities in a little while. Someone's saying, hi Doug, hello William, nice to see you again. Presentation sent to our email. Presentation will be sent on request. Okay. I think I'm going to have to call time on the questions for now. If I haven't got round to your question, there's still a few remaining here. Please email me, and I'll do my best to answer you offline. I'm sorry, normally there's like one or two questions, but I guess because there's quite a lot of people on the call, and maybe you're all keen to learn for the new year, there was more to get through. So I'm sorry, it kind of disrupts the flow a little bit, but I tried to answer as many as I could. So, whereabouts were we? We were looking at the simulation results, and so once we've run the simulation, once we've got our scenarios here, what we can then start to do is we can then start to do some sensitivity analysis. So someone else asked about top rank and finding the critical factors, and actually if we go to this little icon down here, this is our tornado graphs, and so this is a way of showing us what the key drivers are in our model. And so what this is showing me is that by far and away the most significant factor which is having an impact on my total project cost is the cost of buildings, followed by other general overheads, land, raw materials, and so on down the list to vehicles, which is just not very significant at all. So this is saying that the variation around the cost of buildings and how much the buildings cost is the thing which is really driving whether our project is going to come in under budget or overshoot horrendously. So if we take a look at that, let's see what that means. So this is a scatter plot, and on this scatter plot we've got 10,000 different samples plotted. So those 10,000 scenarios which we just ran with At Risk have been plotted onto here, and along the x-axis we've got what the cost of buildings was, and along the y-axis we've got what the total project cost was. So we can see that when the cost of buildings is at the low end of things down here, so our project cost is low. When the cost of buildings increases, so our project cost increase, which of course is what we'd expect, but it's still kind of quite nice to be able to see that kind of relationship. And At Risk is very, all of the data, etc., is very, very open. You can pull out any of the at-risk data and do analysis on it. So it's not some kind of black box that you kind of have to take on trust that it's doing the job correctly. You can analyse the data. So this is showing us that there's a pretty strong relationship between the cost of buildings and the cost of the total project. Whereas if we go down here to the cost of vehicles, you know, we can see that. Where'd that go? We can see that there's very little relationship between the two. There's cost of whether the cost of vehicles is high or low, it's not really having a huge impact on our total project cost. So the way to start to interpret these graphs is that well, I suppose in the most simplistic fashion, the ones up at the top of the tornado are really the things that we need to concentrate on as cost engineers or controllers or risk managers at controlling and mitigating or hedging against, etc. We also have on here the spider graphs as well, which also are an alternative way of showing that sensitivity information as well. So once we've then done that kind of analysis, once we've then found out what the key drivers are, then what's quite a common thing is to want to know what happens in the event that those key factors spiral out of control or are at the high or low end of things. What does that then mean to our overall model? And so one of the things that we can do is something called a stress analysis, which is it's down here as one of the advanced analyses, but it should be one of the more common analyses. And what this enables us to do is to look at what happens when one or more of our costs, in this case, is at the extreme end of things. And so normally, when the software is taking samples, what it was doing with the cost of buildings, it's taking samples from all across this distribution here. But with the stress analysis, what we do is we run two simulations rather than one. We run the baseline scenario, which is where the software is taking samples from everywhere across the distribution as it was before. And then we also look at a stress scenario. So this idea of stress testing is something which has been talked about for the last few years, really, in conjunction with banks and making sure that they've got enough capital, their capital adequacy ratios are sufficient to withstand financial shocks and so on. But what we would do with the stress analysis is we would pick a point of the distribution and just look at a little subsection of it. So what I'm going to do with my stress analysis, I'm going to take a look at what would happen in the event that the cost of my buildings is in the top 10% of cases. What does that then do to my distribution? And so when I do that, at risk, all it's going to do is it's just going to take samples from this kind of little region down here. It's not going to take samples from anywhere to the left of this graph. Those are ignored totally. All it's going to do is just focus on this little area down here and take samples from this little subsection of the graph. And so what I would expect to see from this is that my cost is a lot higher because the cost of my buildings is at the high end of things. So let's take a look at what actually happens. So I'm going to go down here, I'm going to go to Advanced Analysis, Stress Analysis, and then I'm going to add in the distribution I want to stress, which is buildings. I want to see what happens if it's at the high end of things. I want to see what happens if it's between the 90th and 100th percentile, or the upper decile. So if I now click OK and then Analyze, At Risk's now running two simulations instead of one. So if you remember, the first one is the baseline scenario, which is where the cost of buildings was as I expected it to be. And so if we look at the graph here, we've got a 26.5% chance of finishing this project within our budget. If we also look at the stress analysis, then all of a sudden things look a lot less appealing, because the curve has just jumped heavily across to the right. We've got absolutely 0% chance of finishing this project within our original project budget, and the cost of this project is likely to increase significantly. So if we look at the comparison between the two, all of the different comparative statistics here, from the P1 up to the P90, etc., things look worse for the stress simulation than the baseline one, which is once again what we'd expect. But it's I think this is still very nice. It's a very elegant way of being able to show what happens in the event that one or more of our inputs is at the extreme end of things. And you wouldn't necessarily just use this for cost. You could, if you're building up a model where you also have revenues, then you might want to simulate what happens if your revenues are lower than expected for some reason. So this is the stress analysis, a really useful part of At Risk, I think. Now, one of the other things that we can do with the software is look at building in relationships between input variables. And the way we do this, because it's this world of probabilistic theory, is through the use of correlations. So someone before said, how would you, what distribution would you use to estimate demand? And one of the things which kind of impacts upon demand is generally or often going to be the price. And so if we let's draw something here again. If we have let's say a value here, a little kind of graph, and this is my kind of price going up here. This is how much I might charge. So this is impossible to draw with this sort of thing. So that's my price. Then demand is probably going to look something like that. So as your prices increase, so your demand drops off, and you might compare the two and look to try and optimize the point at which your revenues are highest, taking into account other factors, etc. In the case of our cost models, often there's a relationship between one or more cost elements within a model, and so it's really, really important that we capture those relationships if they exist, because the whole purpose of at-risk is to make our models as realistic as possible. And so if relationships exist in real life, and when I talk about real life, I'm talking about the world outside Excel, the world outside the kind of the window. I'm not going to burst into singing Band-Aid or anything like that, but I think sometimes it's easy to forget when we build models that what we're doing is we're looking to build models that represent reality and represent real life. And so where there's a relationship between things, we need to capture that, and we capture that through the use of correlation. So another example might be the cost of, let's say you're working in the construction industry, and all of a sudden the price of steel increases because there's a construction, this is maybe more relevant a year or two ago, but there was more of a construction boom, and so there's more demand for steel, or less supply of steel, or whatever, and so the price of steel increases. But let's say we're building up a model where steel is an input, but then maybe steel pipes is an input as well, and so there's going to be a relationship between the cost of steel and steel pipes. And so if we simulate steel being at the high end of things, we should also simulate steel pipes being at the high end of things as well, because otherwise what happens is we come up against something called the central limit theorem, which means that stuff collapses back towards the mean. And so what typically happens is that if correlations exist and we don't capture them in our model, then we would typically underestimate the tails of our model. What I'm going to do, I'm just going to put in a little correlation here, and what I'm going to say is that I want there to be a correlation between the cost of, let's say, land and buildings. Now, correlations can be negative, such as in the case of our price and demand example, where if one increases, the other tends to go down, or they can be positive, which in the case of steel and steel pipes would be the case, and also in the case of land and buildings, for the sake of argument. So what we're doing here, with the use of correlations, where we're really specifying the strength of that relationship. Correlations are between -1 and +1. So +1 would be this perfect correlation, -1 would be this perfect negative correlation. Often what a lot of companies do is kind of have bands. So rather than necessarily needing to get too concerned whether it's 0.5 or 0.52 correlation coefficient, lots of companies just break things down and say, okay, so whereabouts are we? So 0 is no correlation, 0.2 is a medium correlation, 0.2 is a mild correlation, 0.4 is a medium one, 0.6 is a strong one, 0.8 is a very strong correlation, and so on. And you can do various tests to see how much difference the different correlation coefficients make as well. But just to kind of make it into more of a kind of band thing rather than needing to get too worried. Of course, if you've got historic data, you could use something like the Corel function in Excel to derive that. But I'm just going to say that this is where I want my matrix to be, down here. And now I've got a little correlation matrix where there's now this link between land and buildings. That's been added to the functions up here. You can see there's this extra bit of function added saying there's now a correlation matrix in play, and now there's a link between land and buildings, and so now when the cost of land is sampled at the high end of things, so the cost of buildings will be sampled at the high end of things. And you could actually use something like a risk sim table function, which unfortunately I haven't got time to model here, to show what the impact of the different levels of correlation would be. Okay, so that's the correlations. Let's get rid of it for now. I'll take a very, very quick look to see if there's any questions that I haven't covered, which I should get to. What's the price at risk in Africa? Okay, so I'm just trying to see. Someone's saying, how did you get the stress distribution? That's under advanced analysis and stress analysis. Someone's asking about management reserving, etc. We've got 23 minutes left. I need to show risk registers, and I need to show a couple of other models. So I'm probably going to pass on any of these questions. If by the end of the session I haven't answered your questions, please send me an email, and I'll do my best to answer them for you. But up until now, what I've really been talking about is a cost estimate model. You know, uncertainty around cost, and each of these cost elements, we know that as part of the project we need to pay for these different cost elements, and there's some uncertainty around how much each of them cost, but ultimately we know that we need to make sure that we budget appropriately for each of them. But there's a separate category of things which we would typically call risk events, which can also have an impact on the cost of our project. And so I've got, let's try and get it all on screen. Okay, so down here I've built in a little example of a risk register. So risk events are events which may or may not happen, but if they do happen, they're going to have an impact on how much it costs us to fulfill this project. So I've identified 4 risk elements which could potentially impact upon my project: earthquake, bad weather delays, worker strike, or terrorist attack. Now, for each of these, so with a risk register, what we're typically looking to do is we're looking to quantify 2 elements. So the first is how much is it going to cost if this particular risk happens. And so for that, I've already built in a little probability distribution. Incidentally, if some of you are looking at this and wondering why the cells are coloured blue and some are red, the blue ones are the input distributions and the red ones are the outputs. And you have this option up here in at risk 6.3 to colour the cells, and you could say exactly what colours you want to apply to your inputs, your outputs, your statistics, and optimization variables, and so on. So these blue ones down here have all got a distribution. So for earthquake, I've got a distribution where ranging from a very minimal impact down here, maybe if it's a low number on the Richter scale, up to this high tail up here. So for each of them we've got a different type of distribution. We've got PERT distributions, log normal and triangle distributions, and so on. So you can mix and match your distributions instantly. Some people I think maybe don't know that you can have all the different types of distribution. You can put them all into a model. You don't need to stick with just one type of distribution. And certainly when we're looking at costs and risks, etc., sometimes it's really not appropriate to use the same distribution. Sometimes a log normal distribution is more suitable than a PERT distribution, for example, and so on. But so what we've got a distribution for each of these different risk events down here. Now the second part is of a risk register is the likelihood. So how likely is it that a risk is going to happen? And so for each of these risks, we've given a percentage as to how likely they are to happen within a given time period, let's say a year. Now, what a lot of companies do is they would just multiply the impact by the likelihood to come up with this average risk amount. So here, the average cost of an earthquake is going to be 500, average cost of bad weather is going to be 187, work strike 220, terrorist attack is 150, meaning that the amount that we're going to set aside in the budget for risk is just over $1 million here. But of course, this isn't really an ideal way of doing things. It's all very well if you're running like a large portfolio of projects where certainly things might then tend towards this average value down here. But on a case-by-case basis, what this doesn't allow us to do is to capture the conditional relationship between risk events and the risk register. And actually, if we look down here, so this is let's say hypothetically we assigned just over $1 million to the budget for the risk events. Well then, if we look at these values here, this is the average or the expected value. There's a probability distribution behind it, but this is the average value. And actually, if any of earthquake, worker strike, or terrorist attack actually occurred, then we haven't got enough money in the pot to cover that. And so, what this doesn't do, this average doesn't allow us to capture this conditionality. And so what we're going to do with that risk is we're going to simulate the likelihood, and we're going to tie that into the severity to get this conditional relationship between the two. So I'm going to go to define distributions. When we were looking at cost, we were talking more about continuous distributions, which are the blue ones. But for the risk events, I'm going to look at the discrete distributions. Normally I would use a binomial distribution, but I'm going to use a Bernoulli, which gives exactly the same response as long as you just want one draw. And so what I'm going to do now, well, an example of a discrete distribution, first of all, would be if I flipped a coin in the air and called heads or tails. You'd have a 50% chance of guessing right if you called heads. You'd have a 50% chance of guessing right if you called tails. And actually, if you represented that in terms of a probability distribution, where heads was 0 and tails was 1, this is what it would look like. You'd have a 50% chance of heads, 50% chance of tails. In the case of my earthquake, there's a 10% chance that my earthquake's going to happen. So if I just say I want that to be the parameter, then I've got a 10% chance of the earthquake occurring and a 90% chance here that it's not going to occur. And so now if I start tapping the F9 key, what you'll see is a series of 1s and 0s, and 9 times out of 10 I'd expect to see a 0, and then 1 time out of 10 I'd expect to see a 1. So why am I doing that? Well, what that now means is that actually if I just edit this, now I've got this conditional relationship. So now if the risk occurs, then a 1 is here, and actually because I'm multiplying the contents of this cell by the contents of this cell, if I get a 1 then it gets counted, if I get a 0 then it doesn't get counted. So this is this idea of this conditional relationship. So if I just drag this down here, so I've got distributions here, and so if I now so I'm now simulating 1s and 0s, and so what I'm going to do, I'm going to say that this is something called a risk make input function. This is one of the kind of special functions about risk, if you like. And what I'm doing here is I'm basically telling at risk that I want to treat these two inputs as one combined input. And the reason I'm doing this is for the tornado graphs, which I'll explain in a little bit more detail. But so now what we have this relationship between them. So if the risk occurs, it gets counted. If it doesn't occur, it doesn't get counted. And so now we can run a simulation for our risk register. And so if I click Start Simulation, then let's look at the results down here. So now this is my risk register. So this is those samples from my risk register counted on here. And so what I've now been able to do is I've now been able to apply this to my cost model. Well, obviously you could use this in so the idea of a risk register you can use on its own, or in this case I want to apply it to this integrated cost risk register model. but the outputs from this are the same as up here. We have a range of values, and we can derive our confidence levels for that range. But what I wanted to do here was actually to show what the impact of the risks occurring to our project model. So if I go to my results, here's my original project cost without any risks applied to it. What I'm going to do, I'm going to add an overlay. I'm going to add this one here, and now I've got a model with the risks applied. Let's show it with a cumulative instead. So we can now kind of see the impact of that model, so of the risks. So whereas before I had a 26.5% chance of coming in under budget, with the risks added to that decreases to 15.5, and so the upside increases a bit. Let's just turn off. There we go. So we can now start to look at the two different scenarios. So both with and without risks, and we can look at how the confidence levels change when we apply the risk register. And so actually, what I've done up here, I've just built in some little functions. So at risk has got lots and lots of these little statistics functions, and what I'm doing here, I've just used some of these simulation statistic functions to give me some different values down here. And so what we've got, so here we've got the P75, P90 and P95, and so I've got the project cost before any risks were added, which is these values here. I've got the risk cost, and then I've got the total budget. And so how to kind of interpret these values is that if I had a project budget of 20.893 million, then I would be 75% confident that I would manage to complete this project within my budget. This would be my P75. If I had 22.642 million, I would be 90% confident that I could complete this project within my budget. And if I had 24.5 million, then I'd be 95% confident that I'm going to be able to complete this project within my budget. And actually that 95% there equates to this value here. So it's the distribution. So the red one was the original cost estimate without any risks. The blue one is with the risks added, and so that P95 is this point here. So in 95% of cases, I would have enough budget to complete, and then there's a 5% chance that I'm going to overrun. And actually, we can start to, how much would we need for our 99%, or 99% confident? Then that we'd have to allocate 28,948 to the budget. So this is the first model that I wanted to show. I've kind of managed to hopefully show how you can apply at-risk to a cost model and to a risk register. What I want to do now is just show a couple of other examples of how you can apply risk register. It's a very, very powerful tool which can really be applied to many things, not just a cost model. You could apply it to a reserves estimation model, to MPV analysis, to schedule risk, lots and lots of different things can be you can apply a risk register to. And so I'm going to show a couple of other models quickly. Let me just see. Yeah, okay. I'll tell you what I'll do. Let's do this the other way around. I'm going to show a couple more models, and then at the end, if there's some questions outstanding, I'll zip through them. So let's close down this model. I'm going to show an example of a risk register here. This is just another example of a risk register. Here we've got risk workshops that sat down and identified some different risks. Each of them has been given a different impact. We've got a probability. We've got a range of uncertainty for the cost. So this is really the deterministic side of things. And then on this side, this is the probabilistic way of looking at things. Now there's an extra element here. This is, will it occur more than once? So some of these risks can only occur once. So they're kind of yes, no. Does this risk happen, yes or no? But some risks, they can happen on more than one occasion. And for that, we've got different types of distribution. We've got something called a Poisson distribution, but we could also use maybe a discrete distribution instead, where risk events can happen more than once. And if they happen more than once, they get counted more than once. So some of these, let's just see if I can find a sample that's higher than. There we go. So this event's happened twice, and so it's been counted twice rather than once. So, so it is possible to build up risk registers where things happen more than once. But the reason I wanted to show this model very quickly was because I've also got on here mitigation as well. So typically what we would do, we'd run a simulation. Let me just run a simulation so I've got some data going on here. I think I've got a lot of data in the background here, which is why that one's running a little bit more slowly. But once we've run our risk register and we've looked at the risks, then we can start to decide how best we want to look at mitigating against them. Actually, incidentally, the reason I use that make input function is because if you don't, then these labels here and displays on, you get some funny results on the tornado graph, which is generally driven by whether or not the risk occurs. So it's a good idea to combine them. But once we've identified the risks, then we might want to look at mitigating them. And so here, what we're doing is actually, we're modelling the efficacy of mitigation strategies as well. And so we're able to then look at both pre and post mitigation. So here we've got two different simulations, or we've got a simulation that's being run where this is our unmitigated risk register, this is our mitigated risk register, and then these are the comparative results that we get back. So we can start to analyse how much, whether it's worth mitigating certain things and how much value we get from this as well. Actually, if I can send around some of these models afterwards as well, if people want to get a copy of the models. So that was just a quick look at a risk register which has got risks which occur more than once and which has also got a mitigation model built into it. And finally, I'm just going to show another example of a risk register, but this one is being used in conjunction with a cash flow model. So this is a cash flow model. This is an NPV model where, well, here we've got the deterministic cash flow. This is the probabilistic cash flow, where we've got a number of different things: investment, sales, costs, inflation rate, etc., which all combine to give us this cash flow here. And so we're getting revenues, we're getting costs and cash flow and so on. And so this is what we call an NPV model. I'm sure some of you are familiar with the idea of an NPV model, net present value, which is a way of looking to value certain, in this case, projects, etc. And so this is, if I run a simulation, then typically if the NPV of a project is positive, then it's worth investing in, or monetary theory would say that you should invest in it. And so here, there's only a 3.6% chance that this particular project, that the NPV is going to be negative. So this looks like a really good bet. But what we've got here is, what we've applied to this particular model is we've also applied a risk register in the background. So risk registers can be applied to pretty much any type of model in question. And so here we've identified a number of different risks. We've got a yearly probability of occurrence, which has been derived from, we've tried to figure out how often, what the frequency would be of these, or the likelihood of any of these events occurring. So we've got this yearly probability of occurrence. Here what we're doing is we're simulating the impact. Here what we're doing is, so this is the impact. Here we're simulating the frequency, so how likely it is that the events are going to happen within a given time period. So we're generating lots of zeros, ones, twos, threes, etc., depending on how the risks have been set up. Here we're generating the magnitude, so how much it's going to cost if any of those risks occur. And just like my model before, what we're doing is we've got this conditional relationship. So if the risk doesn't occur, then it doesn't get counted. If it does occur, then it does get counted. So if we look at this top one here, this expropriation, if expropriation occurs, then what we're saying is that the business doesn't continue. And so here it's being simulated as happening in the 4th year, and so after year 4, none of the other risks occur because the risk, the kind of the big risk, the expropriation, has already happened. So this is a risk register in the background here, and what we've got down here on the first page is something called a risk sim table function. And what this sim table is allowing us to do is it's acting as a switch, and the switch is basically telling us whether or not to include the strategic risks from this risk register in our MPV model or not. And so actually I'm going to set the number of simulations to 2. I'm going to run the simulation. I'm going to let that run through. Okay, so so this is our MPV with no strategic risks considered, and then this is the MPV with those risks, with that risk register applied to the model. So a sim table is another way of being able to run multiple simulations and look at what happens across those simulations. And so if we now apply the risk register to the model, then actually we've got almost a 1 in 4 chance of the MPV being negative. So it's a really useful way of being able to, a risk register is a really useful tool for being able to show the impact of risks upon any type of model. Now, I think I've maybe finished those last 2 a little bit quicker than expected because I've actually still got 3 minutes left. So, what haven't I talked about? Let me just see if there's anything glaring from the questions here. Someone's asked about project risk. I haven't really got time to look at the project risk. What you may not know is that on the Palisade website, we have a whole load of these webcasts which have been given previously on here. So actually, this page takes an eternity to load up for some reason. I'm not quite sure why, but this is our webcast archive. So let me just show you where it is. So you can find this under support, videos, and then webcasts. So this is where you can sign up to all the future ones, but if you scroll down, this is a webcast archive. In this archive there's lots and lots and lots of presentations that have been given both by Palisade staff such as myself, but also by some of our clients as well. So if you look on here, there's some various introductions to using the MS Project functionality, because you can also you can use at-risk in conjunction with Project as well as Excel. If you want to look at using VBA and XDK, so when someone asked about how do you customize the ribbon, this is an example. This presentation explores how you can go about doing that. You've got cost estimation and risk registers using at-risk. This is one of my colleagues, Raphael. I'm sure it was a very good presentation. You've got them in different languages, you've got them in different industries, pharmaceutical, agriculture, oil and gas, and so on. So this is a really good resource for finding out more about different niche applications or different functions, etc., without risk. So this is in the webcast archive. So once again, go to support, videos, and actually under videos you've got lots of different getting started, quick tours of the software, and so on. Okay, let me just go down and check. So there's quite a few people who have asked if they can be included in the list of people receiving the presentation. What I'm going to do, as I said, anyone who's signed up for this presentation, I'm going to send an email to everyone to your email address. Once the presentation itself, the video has been uploaded to YouTube, I'll send around the link. If you also want to receive the PowerPoint presentation, you can just email me at that point and I'll send it across to you, or you can send me an email now if you like, doldfield@palisade.com. Send me an email and I'll do that. Likewise, if I don't get around to answering your question, please send me an email about it and I'll do that. Okay, let's just skip through some of these. Is it possible to work with distributions excluding the tails? Yes, yeah, you could certainly do that. You you can specify the percentiles that you look at. Actually, Reg, I'm sorry, I'm not going to answer you fully because you've just reminded me of something that I haven't yet showed, and that's alternate parameters. So, alternate parameters, let me see if I've got one here. Okay, this is an example of sort of like an earlier incarnation of that cost model here. The cost model that I showed before, we were looking at the minimum, the maximum, and the most likely. But sometimes what companies like to do is to look at the percentiles instead. So oil and gas do this quite extensively, where rather than looking at the min, the maximum, and the most likely, instead we look at maybe the P5, the P50, and P95. And what we've got here, we've got a different type of a distribution. So in at risk, if I just show the distribution panel here, you've got these alternate parameters ones here, and what this means is that these allow us to set up distributions using our p-values rather than sort of the regular values. And so if I look at this first one here, this is a PERT distribution, but a PERT distribution normally you need a minimum, a most likely, and a maximum. But for this PERT distribution, using these alternate parameters, which is something I can set up in here in the parameters section, what I'm doing, I'm using the alternate parameters, and I'm saying, okay, so instead of telling me the min, the most likely, and max, tell me what the P5 is, tell me what the P50 is, tell me what the P95 is, and then at risk is then going to convert that into a distribution. So here we've now got a PERT distribution with a P5 of G4, a P95 of I4, and that's now on here. And this is quite a useful thing to be able to do in terms of, someone else asked, Sylvia I think it was, asked a question about how best to judge the min, most likely, and maximum, etc. And actually sometimes when you're talking in terms of minimum, most likely, and maximum, you need to be quite careful that that you're building a mod, that you're really applying true minimums and maximums as you understand it, because quite often it's, you know, if you said to me, okay, so what's the maximum you spend on groceries in a given week, and we have a horrendous shopping bill at home. We seem to spend money like water when it comes to shopping, and so it might be, you know, £300-400 a week, something like that, on groceries. So I might say, okay, the maximum I'm ever going to spend on groceries is £400. But then if you said, okay, so would you ever spend £401? And I'd probably say, well, yeah, I suppose I could, you know, I'm sure I could spend an extra pound somewhere on an extra tube of sweets or something. Would you ever spend 402? Well, yeah, I could possibly do that. And so when we talk about minimums and maximums, it's really important to understand how that these are the absolute extreme values, and sometimes if you're trying to build up a model, then using the alternate parameters is a good way of getting around that, because it really forces you to think in a different way. So to say, okay, so what value are you confident is not going to be exceeded 95% of the time, and what value are you confident you're going to exceed 95% of the time? It's a different way of looking at things. Using confidence levels forces you to kind of think in a different way, and it's quite a useful thing to be able to do. So incidentally, I know that we've now kind of breached that 90-minute mark. The session was set for an hour and a half. I think I've actually managed to cover most of what I wanted to cover within that time. So if anybody wants to shoot off, then please do. I thank you all very, very much for your time. It's really good to have, we really like running these sessions. It's always good to have a large number of people signing up, lots and lots and lots of questions. So if anybody wants to go, please feel free. As I said, I'll make the recording available afterwards if you missed any of it, or if you want to watch any of it again. I'm just going to pick a couple of other questions, and then I'm going to go and make myself a cup of tea and rest my larynx for a little while. Let's see. How do we model customer flow in a restaurant? Well, customer flow in a restaurant, well, something like that, I guess you might have historic data. You might, even if you haven't got historic data, you might be able to sit down and break things into different time periods and look at how busy you are in a particular time. You might have historic data that you can fit distributions to, etc. Let's see. So I'm aware that some of you, I'm just not answering your questions because there's not really time to look at those. Let's see. Lots of people asking for files, etc. Lots of people saying, please send me the models, please send me the presentations. You never use a normal distribution. I'm not sure, Lone or Lone, I'm not sure how you pronounce your name. That indicates that you've maybe seen these before, or maybe I mentioned earlier on, I never tend to use a normal distribution. I would never ever use a normal distribution certainly for a cost model. The reason I would never use a normal distribution for a cost model is because of the distribution itself. So if I open up a normal distribution, okay, so a normal distribution, we require two parameters. We require a mean and we require a standard deviation. So the mean would be the average, and then the standard deviation. So standard deviation, standard deviation, as human beings, I think that we are reasonably well equipped to conceptually understand minimums, maximums, even P5s, P95s, etc. But when you talk about a standard deviation, it's a fairly abstract concept, particularly if you haven't got historic data for most people. So needing to give a standard deviation, I don't think is a particularly helpful thing to do for when building up. Just from a pragmatic point of view, it's a hard one to model. But the real reason I would never use a normal distribution for a cost model is because of this. So these are the theoreticals. So a normal distribution has got a theoretical minimum of minus infinity and a theoretical maximum of plus infinity. Now, I grant that some costs there could be a theoretical maximum of plus infinity. I mean, it's incredibly unlikely, but it's a possibility, I suppose. I mean, infinity's by its nature you're never going to get to it, but you can have an incredibly long tail on a cost distribution. But what you're never going to get on a cost distribution is a negative like this. Your costs when you need to build things, when you need to buy things, you're never going to have negative costs. And so for me, it's a distribution where part of it just isn't relevant. And even if let's say we go to 100 up here, then the probability of it being less than 0 is going to be very small. But it's still a theoretical possibility. So if you feel the need to work with means and standard deviations, then when you're looking at cost models, I would suggest that instead of using a normal distribution, you use a log normal distribution. And a log normal distribution, you will note that the theoretical minimum is 0. So you're never going to have these negative values associated with a log normal distribution. You can still have a long old tail, and you've still got the theoretical maximum of plus infinity, but you're not going to have a negative. And so for me, a normal distribution is just not a good one for costs. So let's have a look. See. Someone's asking about what price you would use for crude oil in view of the current dwindling crude price. I mean, this is a model on looking at costs and risk registers. So kind of modelling crude oil price isn't really something that I feel particularly equipped to do. But you could use something like the alternate parameters to set something up. I mean, what I've done myself, I've set up, so this is a bit of a diversion here, just kind of talking about oil price. I actually set up a distribution for oil price. I've got lots of customers in the oil and gas industry, so I set up the at-risk library enables us to set up distributions for oil price, and this is what I set up a year or so ago, where I said, okay, so my P5 was 80, my P5 was 95, was 142, and my P50 was 100, which just goes to show what I know about oil price, considering it's now more like $50 a barrel. So you could set up something like an alternate parameter one. You could look at historical data. You could even use some the time series feature of at-risk to do that. We've got the ability to if you look in the example models here, example spreadsheets, and then go to time series, there's an example model here which looks at petroleum prices, and so it uses historic data from 2005, I think, to 2011, and then you can use that to fit a time series. And actually, I fit this, and I think the absolute minimum of the P0 came to about $42 a barrel or something like that. So it's kind of just about within the envelope. Yeah, I'm starting to waffle a little bit. I really need to get myself a drink. Thank you once again all for your time. For anybody who's still sticking around for this, but I'm not quite sure how many of you are left. I've still got 85 people left on this call, which is remarkable. So to the 85 of you who have made it through to the very end, thank you very much. I really hope that you found that a useful presentation and enjoyable. We'll send around the link to the presentation. If you need the PowerPoint, send me an email. If you've got any questions at all that I haven't answered, then please send me an email. I'm really sorry. I know there's some questions that are left outstanding. Send me an email, and then I will either answer them myself, or I will ask one of my colleagues if they look after your sales territory to look after it. Thank you particularly to IAV Morocco, which I think is a university in Morocco. There's 14 people watching around there, so thank you all very much to you. And yeah, everyone else, thank you all for your time. Any questions, let us know. But hopefully we'll see you again on one of these webcasts in the future. Okay, thanks a lot. Bye bye.